Howdy! This is your friendly neighborhood physics teacher here. Now, you just hopefully got done watching the video over torque itself. Now we're just doing practice problems, different types of practice problems. The practice problem with Hannah and Leo is a very simple seesaw. But you have some other different examples out there that could pop up, and I just wanted to make sure I go through all the different types that you could see. So the first, another type is we have just a nutcracker. So you can see that you have two different, it's kind of like scissors. Another way you can think about it is scissors. And you have two different kind of forces here. So you have one that's going here and one that's going here. And of course the handle a whole lot longer than you would have where the nut is. Now, if you're looking at the PowerPoint, it says that where you put the nut is 1 centimeter. And then from where the joint is to the end is 10 centimeters. So you kind of have you have your two different lengths there. And then another information, it says that the amount of force that you put on it to kind of crunch it is 20 newtons. But we want to know, what is the force that's happening this direction? So if you put 20 newtons this way, you can see how the line is connected. And how that affects the force going up. How that affects the force going up. Now, remember, there's some key things there. First, we have to figure out where the pivot point is. Hopefully you realize that it kind of pivots. And this one doesn't fully pivot. It just, I guess it doesn't fully rotate. It just kind of moves a little bit. But like where the joint is, kind of like the door hinge. So that would be our pivot point. That would be our pivot point. And so we'll call this force 1, and we'll call this force 2. So our force 1, let's pull information for our force 1. For force 1, we don't know what it is. So we don't know that. But our distance for force 1 from the pivot point is 1 centimeters. Do we like centimeters? No. We do not like centimeters. We need to convert that into meters. So there's a couple of ways you can do it. You can do dimensional analysis. You can do the exponent way, or you can just move the decimal. Hopefully you know that centimeters is 100. There's 100 centimeters and 1 meter. So basically you're dividing it by 100, or you're moving the decimal over twice, and you're getting a 0.01 meters difference there. So, and if we go for F2, our newtons is 20, and our distance to is 10 centimeters. But again, we don't like that centimeters, so we have to divide it by 100, and we move it over 1, 2, and we get 1.10 meters for our distance. So we have all we need. We have our force and we have our distance. Now we just need to know which one's clockwise and which one's anti-clockwise. So we kind of have the arrows where it's going. So if this one's going this way, if it just kept spinning around the pivot point, that would end up being clockwise. This one, it's going this way. This one kept spinning. It would be counterclockwise. Real quick. Check on the PowerPoint real quick. I feel like I wrote down something wrong. Nope. So yes. So then that would be counterclockwise because we figured out our clockwise one. Sorry about that. Want to double check something. So now we know our torque from our clockwise equals torque from our anti-clockwise. F1 is our anti-clockwise. F1, D1, F2, D2. And honestly, when you just have one on each side, it doesn't matter. When you start getting into more forces affecting it, that's when it matters if it's clockwise or counterclockwise. As long as you know one's on one side, one's on the other for these types of problems, you're golden. But when it gets a little bit more complicated, like you have one pushing up, one pushing down the same side, then you have to figure out which one's clockwise, which one's counterclockwise, and that fun stuff. But these are pretty simple as long as you realize one's on one side, one's on the other. So force 2 is 20. Distance 2 is 0.1. We're looking for force 1, and distance 1 is 0.01. So you solve for what we got. So we have 20 times 0.1, and that just gives you 2 equals force of 1 times 0.01. We need force 1 by itself, so we divide what we do to one side, we got to do to the other. So our F1 ends up being 200. Woohoo! So think about it. That's why scissors, that's why little contraptions like this are made. So you can put a lot of force further out, and then that transfers a heck of a whole lot more force closer in. That's why we've invented little things like this. Let's go to our PowerPoint and see what our next problem is. Next one is looking at a crane. So we have a crane, and I'm letting you know that the pivot point is kind of at the end of the crane arm. And then you have for where the force, like where an object would hang on a crane, and most cranes have some type of little help for the arm to give it a little extra support. And we're just trying to figure out how much support that little lever needs to be if we're picking up a load of 40 kilograms. So let's go to our scratch paper here so we can give us a little visual. So we have a crane arm, and we have some type thing hanging there, and then to kind of give it a little bit of support, we have a support arm there. So the first thing we need to do is figure out where our pivot point is. I already kind of gave you a hint, or kind of told you already, that our pivot point is at the end of the crane arm. Of course, the force, we'll call this force 1, is going there, and it was blue. Force 2, nope, quit. Force 2 is kind of going here. And we're going to, I know I didn't draw it, but we're going to pretend that's at a 90-degree angle. So if this is our pivot point, we need to figure out the distance. And I believe it did tell us that information. So this distance was 2 meters. And then this distance was 0.8 meters. And it did give us the mass for the load it's picking up, which is 40 kilograms. So that's information. So we have the mass, we have the distance for force 1, and we have the, we don't have the force of force 2, and we have the distance of force 2. So there we go. We need to figure out what that force for force 2 is. Before we do that, we need to figure out which one's going clockwise and which one's going counterclockwise. Now, this is the pivot point here. The pivot point's over here. So as this one rotates around the pivot point, so we're going around the pivot point, that would be a clockwise manner. The way this one rotates, again, around the pivot point, would end up being a anti-clockwise manner. So all of our F1s, mass 1s, and all that, that's our anti-clockwise. And then our F2s end up being our clockwise. So if we do our equation here of clockwise equals anti-clockwise, so that would be F2 D2 equals F1 D1. Now we're looking for F2, so that stays there. We have D2, but we don't have F1. We don't have F1. Remember, that's just our force of gravity. So we can figure out our F1 equals mass times acceleration due to gravity. Our mass was 50. Acceleration due to gravity is 9.8. So you just plug that into your calculator, 50 times 9.8, and it gives you, again, 490. You can just plug that into your problem here, 490, and we have our distance, which is 20. Now you just solve for your F2. Just turns into algebra at this point in time. We need F2 by itself, so it's being multiplied. The opposite of multiply is divide. What you do one side, you gotta do to the other. So that arm, that little extra little help there, needs to do this much force to give it support, to keep it from like breaking, basically. So there we go. So if you plan on building machines at all, guess what? You need this. Let's go back. Let's do another practice problem. So the next practice problem we have is if the seesaw isn't quite lined up. So most of the seesaw methods we've done so far is our pivot point has been in the middle. So if our pivot point isn't in the middle, we have to take the mass of the arm into consideration. So if we go back to the crane, in theory, I missed a step. I should have taken the mass of the arm into consideration. But I just wanted to get you some practice problems there. So for this one, we have to take the mass of the lever arm, or in this case, the seesaw, into consideration because the pivot point isn't right in the center. So we're going back to Hannah and we're going back to Leo, but this time the seesaw has been broken or just not put together right. So we have 3 forces to deal with instead of just 2. So this is why I said it matters if we're going clockwise or counterclockwise. So we have 3 forces we're dealing with. We have to take the mass of Hannah, we have to take the mass of the plank, and we have to take the mass of Leo all into consideration. In this case, we're looking for where Leo is. So go back here. So we're going to draw us a little example. Again, you have Leo. You have Hannah. And it gives you the mass of Leo. You have the mass of Leo at 155. You have the mass of Hannah at 60. And you have the mass of the plank at 30. And it gives you the distance. Gives you the length of plank is still 60. And it gives you the distance from where Hannah is from the pivot point to be 4, and we're looking for how far Leo is. So let's write that information down. So we know that, please go away so I can get to my pens. Thank you. We know that Hannah is 4 meters away. And we know the whole entire length is 6 meters. So where would the center of mass be? In the middle. Very good. So the center of mass would be in the middle. Would be in the middle. So it'd be at 3 meters. It would be in the middle at 3 meters. So how far is it off the pivot point? So this is where you have to do a little bit of math here. So if Hannah is sitting at the end and is 3 meters off the center, but the pivot point's 4 meters off, so this has got to be 1 meter. So it's just 1 meter off the pivot point. We were given all the masses, so we have the mass of Hannah to be 60. We have the mass of the plank to be 30, and we have the mass of Leo to be 150. Of course, those are all in kilograms. All the forces that are causing it is going down, so this would just be the force of gravity again. So we need to figure out the force of gravity of Hannah. So that's just mass times 9.8. We need to figure out the force of gravity of the plank. So that's just 30 times 9.8. And we need to figure out the force of Leo. So that's just 150 times 9.8. $60 times 9.8 equals 588. 30 times 9.8 equals 294, and 150 times 9.8 equals 1,470. So those are all our forces. Now we need to figure out which one's spinning clockwise and which one's spinning counterclockwise. So this one be going around the pivot point. That's anti-clockwise. This one's going around the pivot point, so that'd be anti-clockwise. This one's going this way around the pivot point, so that would be clockwise. So Leo is clockwise, and the other two are anti-clockwise. This is why it matters, because if we do everything that's clockwise on one side, everything that's anti-clockwise on the other, so we have force of Leo times distance of Leo equals force of Hannah times distance of Hannah plus force of the plank times the distance of the plank. So if they're going the same way, you just add them. So force of Leo was 1470. The distance of Leo, that's what we're looking for. The force of Hannah was 588. And the distance of Hannah was 4 meters. The force of the plank was 294. And the distance of the plank ended up being 1 meter. Again, you just solve. So this stays over here for now. So then you just do 588 times 4. That gives you a 2,352 plus 1 times anything is just that. So all you do, you have to add 294. So you get 2,646. And they're being multiplied, so the opposite of multiply is divide. And what we do to one side, we gotta do to the other. So then you just divide your answer by 1470. And he should be 1.8 meters away from the pivot point. 1.8 meters away from the pivot point. So there we go. There are some practice problems. You do have homework that's due Sunday that's going over this. If you have any questions, please let Miss Heath or Miss Verona know. Hopefully you have a wonderful day. Bye!